All right, so I'm going to do the lecture now. I understand that people budgeted 20 minutes for lab and they need to go. I totally understand. I think this will take about 20 minutes. You will not hurt my feelings, and I will not penalize you for stepping out if you need to go. My son lives 5.5 hours away, so I know it's like you might have a long drive.
Thank you.
All right, so I think I left off here where I was talking about the fact that circadian rhythms have to develop as the brain matures. And it's not how long since the time you were born, but it's about 16 weeks post your 9-month tuning, right, is when this develops. And so here we begin to see this free-running rhythm, remember that term, free-running rhythm, appearing. And over these 8 weeks, and then down here by week 16, right, we have established a pretty good sleep-wake cycle. Right? You can see it. All right. I already kind of mentioned this, but in the human study, here they did a 12-hour phase shift. And so when we do that, our bodies have to catch up. Our bodies can't just adjust immediately to a new sleep schedule like that. And it takes about 2 days to do a 12-hour shift. So this is why we have jet lag, right? When you guys aren't ever going to be in a lab somewhere and they're going to say, hey, guess what? You need to shift your time by 12 hours. But you might take a plane somewhere and be several time zones away, even 12 hours away if you go around to the other side of the world, right? So crossing time zones takes our circadian clock out of sync, and it takes several days, and the reason it takes days is it's because the light cycle is what helps reset our clock. So it takes several days to do that. It turns out that it's harder to travel, you have more jet lag when you're traveling west to east because you're working against your normal clock, which wants to run long. Our normal clock wants to run 25 hours instead of 24. So if we move from east to west, we're actually going with the flow of our normal clock to be later as opposed to trying to be earlier. Why does this matter? Well, they looked at a study with Major League Baseball, and they looked at how often the visiting team won the game. And they looked at it within the visiting team's own time zone. They won 46% of the time. If the team flies west, they won about the same amount, 44%. However, if they flew east, their percentage went down to 37%, almost a 10% drop in the ability to win. And this is because of jet lag, because it's harder to adjust. This is also why when there's a really big game, when does the team get there?
A few days before.
At least a few days before. Like the Super Bowl, they may be there a whole week, right? And part of that is taking any of this out of play from the game, from their performance. Right? All right, so I already mentioned this. It's easier to shift later because the clock is longer, and so this makes it harder to travel. Traveling west is easier than traveling east. All right. I mentioned that you need this light-dark cycle, right? This is the Zeitgeber, the entraining stimulus to reset the clock. So I want to talk about what is the clock and how do we reset it. So 2 areas that we want to focus on. An area of the hypothalamus that is just above the optic chiasm that's called the suprachiasmatic nucleus. or SCN for short, suprachiasmatic nucleus, SCN. Back here we have the pineal gland. Okay, remember learning that in your anatomy, right? Singular structure back here. And those two are going to work together to help regulate our circadian rhythms. All right? Suprachiasmatic nucleus, pineal gland. All right, so if we take a section through a rat's brain, or a human brain, in this case it'll be a rat's brain, like that, and we look at it, here we see this white thing here is the optic chiasm, and the black areas here are the suprachiasmatic nuclei. They've been stained so that you can see. When rats have an intact suprachiasmatic nucleus, they do this. Right? They have free running rhythm, they have a natural clock that can be maintained even in the absence of light. Right? When you remove the SCN, so here it's been lesioned in this animal, this is what you see. They lose the ability to maintain that free running rhythm. They're just sort of randomly active and randomly asleep. They don't know what time it is anymore. So it becomes random lesion in this area. So those were the first studies that sort of identified. Like I said, a lot of what we know comes from animal lesion studies. You go in and destroy an area, and what kind of behavior do we see? Oh, we lose our clock. That must be the clock area, right? And so then we can now focus our research efforts on understanding what's going on in the suprachiasmatic nucleus to allow us to have these biological rhythms. All right. So again, this is a different study where rat's normal, lesions, suprachiasmatic nucleus, now the rat has random activity. Here, they implanted a fetal suprachiasmatic nucleus that they had got out of another rat into the rat with the lesion, and after several days, the rat starts showing a free running rhythm again. Is it a normal free running rhythm? No. But is it random? No. So again, we can take it out, we can put it back in, and we can show that it's the clock and that it's responsible for producing these rhythms. All right. So the way that it produces these rhythms is through a seesaw sort of balance between gene production of some proteins. And so we start out and clock and cycle, these two proteins come together and form this compound that causes the suprachiasmatic nucleus to make purr and cry and tau. And purr and cry and tau inhibit the production of, or inhibit this clock ability, right? So when purr, cry, and tau are made, they start, the more they're made by clock and cycle, the more they inhibit this, okay? And then they make so much of the purr, cry, and tau that we don't have enough clock and gene anymore, it's totally inhibited. So they quit making purr, cry, and tau. So over time, the purr, cry, and tau start breaking down. And as they break down, it allows more clock and cycle to start going. And as more clock and cycle are made, they start making purr, cry, and tau that are inhibiting it now. And so it goes like with this seesaw, right? High clock and cycle, start building up the purr and tau. Now purr and tau is high, and clock and cycle are low. That means we're not making anymore, so it starts to drop. And as it starts to drop, clock comes back up, and it just goes like this. And it goes like this every 25 hours. That is our clock cycle. That's how we keep track of 25 hours, just through this cycle. And this really kind of walks you through that, right? Now, I keep saying light can reset this. The suprachiasmatic nucleus is directly above the optic chiasm. The optic chiasm sends some optic nerves up into the suprachiasmatic nucleus, and the presence of light, your eyes being stimulated, particularly with sunlight, causes glutamate to be released, and glutamate resets this cycle. It has the ability to stimulate clock and cycle to start making per and tau. So neurons from our eyes actually go up into this area and cause glutamate to be released and reset the clock back. Are we good? If I were you to study this, I would write this out. I would diagram it as a 24-hour cycle. And I can post a picture of that on the middle side so that you really understand, okay, clock and cycle are high. They're starting to make more per and tau. And as per and tau start to build, clock and cycle can't do their job anymore, so no more per and tau are made. Therefore, per and cry and tau are made. And so they start to break down and it goes back and forth. All right. So that's how the clock works. How does the clock regulate our sleep-wake cycle? Well, it uses a lot of different hormones, like VPI, vasopressin, neuropeptide Y. We talked about NPY when we talked about hunger and feeding. So, hunger and feeding are related to our sleep-wake cycle. And so these hormones are probably the things that were being released by that fetal tissue that was transplanted in there to help sustain the rhythms. But we don't know a lot about the circuitry. It's pretty complex for how all of this sort of works. There's other areas that project to the midbrain, to the sleep nuclei that we'll talk about in the next section that helps stimulate arousal or being drowsy. And then finally, we have the pineal gland, connections to the pineal gland, and the pineal gland releases melatonin in the brain. Whoops. And melatonin is a hormone that's going to go throughout the whole brain, and that happens a couple of hours before we go to sleep. So the clock says, hey, it's a couple hours before you should go to sleep, start releasing a lot of melatonin, and that helps our brain calm down and go to sleep. Now, there's a lot of melatonin products that you can buy that claim to be able to help you sleep better. And there's and it's based on the fact that this happens endogenously, right? A couple of things that you should know about melatonin. One, when you take something that you want to affect your brain, it has to go through that whole pathway we talked about with not being destroyed by the acid in your stomach, getting absorbed from your intestines, getting transported into your body across the blood-brain barrier, right? And getting into your brain in sufficient quantity. So we're not really sure that melatonin can do that when it's taken per oral. Like we know when our brain releases it, what happens. But taking a pill and going through all that process, it's not even, we don't even really know if melatonin can cross over the blood-brain barrier on its own, right? Yes, right.
What about the other medicines that can make you sleepy, like Benadryl?
Yeah. Right, so that's an antihistamine, and those can cross the blood-brain barrier. And histamine is a awake chemical in our brain, and so blocking it makes us drowsy. And I'll talk a little bit more about that when we talk about sleep. If you look, I just pulled this off of Google, right? And if you look at these, there's 5 milligrams, 1 milligram, 5 milligrams, 10 milligrams, 10 milligrams. Most doctors that would prescribe melatonin would prescribe 1 to 2 milligrams. So most people that are buying this stuff over the counter as nutritional supplements are taking way more than a doctor would advise that you take, right? So, and what we do know with melatonin supplements is that there's a strong placebo effect. You take something and you think it's going to make you tired, and sure enough, you get tired. Whether it was the thing that made you get tired or the placebo effect, we don't know that.
Is that a bad thing though?
Not necessarily, although we don't know, but I wouldn't take 10 milligrams. I would take maybe 1 milligram, because we don't know what taking 10 milligrams does. That's 10 times what a doctor would prescribe, right? There's some evidence that this may help, that if you're trying to shift your circadian clock, that taking melatonin could help you shift it, because it's a feedback signal. If it's getting into the brain and doing what the endogenous stuff does, it's a feedback signal to our clock, right? But there's less evidence that if you have abnormal sleep patterns, that it's going to fix one night of sleep. Yeah, that's what I'm trying to say. So if you're trying to shift your circadian rhythm, it may be useful, but in terms of helping you go to sleep because you're anxious or have other things that are obstacles to going to sleep, it may not be the best sort of thing for them. And lastly, the FDA doesn't regulate any of these nutritional supplements, meaning nobody tests them to see how pure they are and if they actually have those concentrations. And labs that have tested them have found a huge range from having 80% of what's in there, so instead of being 1 milligram, it's only 0.8 milligrams, right? To having 460% more than what they're saying, because they're not regulated, and no one's making sure that 1 milligram is 1 milligram. And different companies have different quality control, and they don't have to have quality control because nobody checks on it.
So, I know you said they're not really sure if it even crosses the blood-brain barrier. Do they know, like, if taking melatonin in high doses like that, does it cause any negative side effects? Are they aware?
There are some animal studies that say chronic high melatonin use can have some negative effects, particularly on reproduction and things like that. So, I don't know. I'm not a huge expert on that, but I know that there are some negative effects with chronic high doses in animals. All right, that's it. I told you it'd be about 20 minutes.
Can you walk us through the data house?